Thanks again for the introduction and also inviting me for this occasion. I'm very honored. I originally planned on being there in person, but I apologize for not fulfilling that for some personal reasons. But still, I'm very excited. And I will leave my contact at the end. So if any follow-up questions, feel free to follow up with me. Or I believe my colleague, Tamzid, probably is in the audience somewhere. Are you there, Tamzid? Yes. So if you want to follow up about the presentation or what Amazon team in person, please chat with Tamzid. Okay, with that, just a little introduction of the Amazon audio team. So that's where I belong. And basically, Amazon audio team is responsible for the all the audio engineering needs of Amazon devices. So that includes any devices that has the microphones or loudspeakers. Basically, it comes through us. And we have about 130 people team in California, Massachusetts, and Washington. And I belong to Massachusetts, Boston team. And we have a team of scientists working on the algorithms and acoustic modeling, as well as hardware and software engineers working on the implementation of those algorithms and designs. The area of focus includes far-field voice pickup. We designed the microphone arrays and algorithms that goes underneath it to process speech and other signals, either in DSP or machine learning. We also do music processing with 3D audio, and hearables are kind of hot right now. And the up and coming, and then this is kind of focus of today's talk, is the presence and localization for the smart sensing application. So the it's an outline of the talk. I'm going to talk about brief history of the Echo and Alexa, how it started and how it evolved, and also about how Echo actually works underneath. And then I'm going to the main meat of this talk about ambient sensing, ambient compute-related features and technologies that we're developing. And then also some ongoing and future kind of work that we are doing as a kind of discussion point, and some suggestions or comment from you guys. Let me just, I cannot see myself, so let me see if I can fix that. Okay, that's fine. So in terms of how Echo started, this is a scene of Star Trek, and I'm not necessarily kind of fan, or I didn't grow up watching this. This happened in 1960s, although there were some recent like rerun or follow-up shows on these films. But it's one of those iconic like sci-fi shows, and in this what's called the Starship Enterprise, there is this kind of omniscient voice-activated artificial intelligence, or properly named computer. As it happens, a lot of times what's happening inside of what you see in the sci-fi novels or movies kind of inspire people, and then that actually turns into reality. It's one of those things, and Jeff Bezos actually grew up watching this and fascinated by this. And in 2011, he started kind of thinking about doing this as actual product. And you have to remember that 2011 or so, Amazon was not known for high-tech artificial intelligence focused company. we're known for the more of the sorry, the screen sharing still going okay? Hello?
Yes, looks fine. We
Okay.
can hear you.
Sorry. So we only think that high-tech consumer electronics that we had was a Kindle. And so it was a little bit kind of risky and bold move that we envision having a smart voice assistive device. And this is a kind of hand drawing of Jeff himself. I heard, I wasn't there at the time. First kind of depiction of what it would look like. It's a square box with a microphone and speaker and Wi-Fi connection. And they imagine that maybe such a device is voice activated and then can play music or read news or other things online. And another requirement was that it should work anywhere inside of the house and far away. And I mean, there are a lot of challenges to this in many layers, but this anywhere in the house is kind of interesting concept for me as a person works in the more like a voice pickup side of the world. And the original Echo actually came with this remote control. I don't know anyone is aware of that, which quickly disappeared. We shipped the device with this, even though it has a far field capability, because we have very things, we thought it was very risky and people were anxious that it may not work. So you can kind of use a remote control to interact with the Alexa. But it turns out that luckily we didn't have to worry about them. Far field voice speaker worked good enough. So the primary use cases, a lot of people are aware of this. People play music and ask about the weather, news, and joke is very popular apparently. And then the timers and shopping lists, and you can make audio and video calls. And personally, my favorite is, I ask Alexa to ring my phone because a lot of times when I try to find my phone is hard. So I have a Alexa here with me right now. And Alexa, what's the weather?
The current weather is 86 degrees Fahrenheit with mostly sunny skies. Today, you can expect partly sunny weather with a high of 91 degrees and a low of 71 degrees.
Okay, hopefully you heard the Alexa interaction here a little bit. So when I did this, right, and asked weather, and then Alexa came back with this weather. I mean, it's very trivial thing. People do this all the time these days. We kind of take it for granted, but what does really happen underneath? And there's a whole lot of things happen. So I'm going to kind of break down those things a little bit so that you can kind of understand and appreciate things behind the scene a little bit. Now, there are things that are happening in terms of like microphone processing and voice speech cleanup, which I'm going to go in details. So I'm going to skip that. So once that's done, that's what's the weather? That part goes to what's called the speech platform, where we this is kind of manager of all the kind of different shuffling of streams of data and then manage the different interaction with the different modules. And the first of all, since this is stream of audio files and speech, it goes to ASR, speech recognition, and that turns into the text. And the text then gets shipped to the NLU, that's a natural language understanding. So this is kind of the high-flying AI model. They try to understand the meaning of these alphabets. And the meaning, we call that intent. And the intent now gets routed to appropriate like application, because skills or application modules. In this case, it's about weather, right? So it will go and ping the weather forecast server somewhere, and then gets the weather text. And then it also, we need to, I also need to speak that weather forecast, right? So for that, we go to the TTS, the text to speech unit. And then that turns this is opposite of ASR, turns the text into the audio samples, then it gets to the local device, and then it gets played out. So even this little simple thing like this, there's a lot of interactions with the different modules, and this processing happens in different servers across internet. So one of the engineering problems that the people solved was that the latency of things. In order for this to be more conversational feel, right? As if you're talking to someone in front of you, the latency of this interaction has to be fairly small. You cannot have you have to wait 4 or 5 seconds to get the answer, and that's not interactive. So optimizing those latency across all this data stream across the internet was one of the big engineering challenges in the beginning. So now I want to talk about the things that happened just before that, before it gets to ASL and NLU. And this is the world that I and my team tend to live in. So we have the multiple microphones, and originally Echo had 7 microphones, and that gets routed to the first thing that we do is this audio front end algorithm module that does beamforming and other kind of noise reduction and speech enhancement work, including the echo cancellation. And then it goes to the wake word engine. So there's always stream of signal that's cleaned up on an ongoing basis, and this local wake word will trigger the, oh yeah, there was Alexa. Now I have to pay attention. And then the following the speech or audio samples gets to the ASL and other things that I just talked about. And anything that's playback side, the music or speech that is entered, it goes through the same module, but then for the playback purposes. So actually, this is a little simplistic kind of old model in terms of the cloud side, but on device side. The latest versions of Echo, a lot of this ASL, NLU, and TTS actually happens locally. We implemented it because of privacy reasons. Now you can actually, in the setting, turn off any data upload to the cloud, in which case all this thing has happened down to NLU has happened locally. So we developed some of these models, local version. So it's more like a local centric model right now. So in terms of that, all the front end beamforming, ANC, and whatnot. So what are the kind of problems that we are trying to solve and challenges? It's all about the acoustic environment that we are in. If you have a microphone next to you and closed up and speak and talk to Alexa, everything's pretty easy. But far field in a room, there are a lot of challenges. Room is reverberant, right? Especially if further away from the wall, there's more reverberation that makes it hard for ASR to work properly. And there are noises, you have appliances, and TV might be on. So all those noises gets into the as a interferer. And when you play music, of course, the music itself is a big noise source, and we have to reduce that. Now, the one interesting thing about the sensing and detection algorithms, you don't necessarily want noise reduction on them. There are cases you want that, but some sensing algorithms wants to know what kind of noise there is, because that is information that you want. So in that case, the sensing happens before the noise reduction module. And I'm going to go one layer down. this is as low as we can get for this talk. Actually, this is part of the published paper from us. And if anyone needs reference to this, feel free to reach out to me. I can give you the reference. And most of my talk today is coming out of the either blog or the published paper, so I can give you references. So microphone signal goes through the set of the analysis filter banks. So this is frequency domain algorithms most of the times. It goes through some kind of processing of gain or other adjustment, and we do the main kind of beamforming, fixed or adaptive, and also AAC echo cancellation processing, the bulk of noisy reduction. This could be some machine learning algorithm as well. And we do some post signal adjustment, and then it goes through a set of synthesis, and then gets to the time domain, and then it goes to the wake word engine. Now in parallel, under here, the sidechain, we run this any sensing or localization algorithms. As I said, you want to do it before this noise reduction. And that kind of goes into this kind of state control kind of module that tells us whether there's noise, a lot of noise, that music is playing loud. Those states can control the adaptive beamformer or AAC control purposes. And then in parallel, if there's any music playback going on, we have this set of playback algorithm running in parallel. And there's a connection between these two because of the AAC requires the reference signal. So this is kind of the nitty-gritty kind of technical module level of the audio front end. Now, so what does it really do? How much does it do? So I have an example here. And in terms of beamforming, actually, so original Echo was 7 microphones. And now we have many different kinds of Echo devices, all different kind of form factor and size and applications. And so some of them has down to 2 microphones. And in between we have 4, 5, 3 microphones as well, I think. The reason why we have many different kinds of microphone arrays and number of them are each device has different form factor and sizes, and also requirement for the far field was a little near field and the cost. So all these things requires us that we design the microphone array differently. And also over time, we enhanced our beamforming algorithm. So even fewer microphones, we can do more compared to the original Echo. And the AAC wise, we started with single channel, now it's multi-channel. And speaker nonlinearity is always, challenge if you know the AAC world a little bit. But we developed some algorithms to deal with that. So I have an example here. Hopefully you can hear it. This is the first one is without any of this beamforming and noise reduction, and with some room noise as well as the music playback. What does it sound like at the raw microphone before all these things? And it sounds like this. Did it come through okay?
It was really low in volume.
Oh, really? Let me try it again. Is it better?
Not a lot. So in the left bottom corner of your Zoom, where you share screen, you can have an option to share sound. If you enable it on, it will get better.
Right. Let me. I thought I did that. it's talking about audio in the presentation and you have audio problems. Always very interesting. Okay. Maybe I can provide this slide later, and then if you need, you can kind of listen to it afterwards. So, sorry about that.
Sorry.
So now I'm going to talk about the wake word engine. So one of the important thing in this process is that in the constant stream of sound and speech, we don't know this is when the user said Alexa, therefore I'm going to pay attention. So it requires a really highly accurate, like Alexa specific word, ASR, and also you don't want any false positives. False positive can be very annoying. Some random noise or random speech triggers on Alexa, which still happens, I have to admit. So training against that is one of the big thing. And I have to mention that this wake word module itself, we have separate dedicated team working on this, but we work closely. And so I'm going to speak in terms of really high level. What are things that they're faced with. So similar kind of challenges like noise and reverberation and even music playback AC residuals can be challenging for detecting this. And then different people speak differently for Alexa, right? So it's another challenges. And then also this has to be very low latency so that we can detect the Alexa right away. So the model has to be small and optimized enough that it can act instantaneously. Illustrate one of the challenges, I have this illustration of waveforms for Alexa and in good condition on the left. One of the things that you want to do is you want to detect when this utterance starts so that you can look for the remaining samples of audio for the match. And so this is one of the first thing. And when the waveform is clean and noise free, it's relatively easy. But if the waveform has a lot of noise contamination, then even finding where it starts can be a very hard problem. And if you start wrong, then if you, let's say in this example, you start in the middle of this correct Alexa utterance, then the amount of information that you have about detecting Alexa can be much less. So these are the kind of challenges that we go through. And in the early days of Echo devices, the wake word model was more old-fashioned machine learning model. So it has a kind of light neural net feature extraction and phoneme detection kind of layer. And then it has the HMM. This is the illustration of that hidden Markov model for sequencing those phonemes for Alexa. And then we have a final SVM, support vector machine for based on the probability, what is it is final decision of is it really Alexa or not. So this was the early approach, and recently most of the devices are transformed into this deep neural net. So it's a convolutional neural net, and with this, its accuracy and force accept rejection is much higher. So there's a lot of work went into it. And one of the things, of course, that allowed us to go from this old, more modular architecture to end-to-end is the data, right? Creating any kind of deep neural net requires lots of data so that you don't overfit and can generalize. So over time, we had enough data that we were able to train the neural net for the wake word. So now I'm going to talk about the more smart home and ambient sensing and compute related things, kind of technology that we are developing. So currently, over time, the Echo devices in the beginning was very simple. Get the news weather kind of device to operating the smart home, different things in the house. So you kind of evolutionary process over time, and now you can do a slew of things, and you can operate the lights and switches and power outlets either triggered actually by the voice of the user, or if you have some sensor, you can in the background, depending on the trigger, will automatically do that. And there is also home security application where you can have a Alexa device to be kind of, we call the Alexa guard. You can monitor your house. A lot of it based on the acoustic signal can alert whether there is a fire alarm or there's intruder. So the technology that allows us to do this is around the detection and localization. So these are the problems that we are currently working intensely on. So one of the modules is the acoustic event detection, which detects the fire alarm or even glass breaking, dog barking or footsteps or door closing, etc. So that is there any people or animal or intruder in the house? We also developed the ultrasound-based human presence detection. This is about when you are coming in and out of the house, it can automatically turn on the lights, for example, among other things. And then also we are developing the user localization module to support all these smart home related applications. So this is kind of our stepping towards the ambient sensing, ambient compute. It's about having these distributed sensors and compute devices sitting kind of passively in the background without interruption normally. And when it's right time, the user actively ask for it, or based on a set of conditions that users set, or in the future, maybe intelligence is smart enough that it will figure out this is time when you need this and offer right set of information or services. So that's kind of vision for our ambient sensing and compute. So acoustic event detection. So this is not developed by the audio team, but the neighboring team. And then so I can talk about some high level architecture and other things. It's based on the RNN, LSTM, with some fully connected layer in the front. And the feature is the low frequency based energy. So there is it's a two-step process where there is a one in the device and there is a verification module in the cloud. So one of the challenges to this is that the number of kinds of sound we try to detect, it can vary. And then over time, we can add more sound that we want to detect. So how do you create a network that can over time can be scalable to increasing number of different targets without having to retrain every time? So they come up with this layered approach of for each target sound, whether it's glass breaking or alarm, they have a separate RNN network, and they're running in parallel. And then the embeddings of those outputs gets aggregated and then goes to decision tree. And this decision tree is where you decide whether right now, let's say it's past 5 seconds of audio samples, was there just an alarm, or there's an alarm and maybe footsteps, or there's maybe dog barking. So in terms of how many sounds and which sound is decided by this decision tree module based on this parallel output of this RNN. Data is always, hard to get, especially for things like this. And glass breaking was a special hard one. There's not much available glass breaking acoustic data. So they ended up hiring some people and ordered hundreds of different kinds of windows and actually broke them and recorded sound for training. So now I'm going to talk about the ultrasound-based presence detection. This is the one that developed by audio team, so I can go into some details more. One of the requirements for this feature was that without any additional sensing hardware, there was a requirement, which made this thing very hard, harder than if you think we can just add some dedicated ultrasonic sensors and receivers. So that's one of the challenges. So it just uses conventional microphones and loudspeakers on the Echo device, and luckily they are ultrasonic capable. The ultrasonic signal itself is above 32 kilohertz. Exact frequency depends on the device because of the different hardware has a different sensitivity. And we are using Doppler sensing, not the time of flight. And we found this to be more robust in terms of presence application. And Doppler mechanism, many of you already know, it's basically we emit ultrasound that usually around single frequency band. And then we get the reflection off of the any moving objects. And then because it's moving, you get this frequency shift. So that is the kind of signal that we use to detect that there's the person. Now I'm giving you this spectrogram plot of the recorded signal on the device. And the person is kind of moving in front of the device. So y-axis you can think of it as a kind of frequency equivalent. So it's kind of spectrogram. So this line here is the carrier frequencies, ultrasonic carrier frequency of 36 kilohertz or somewhere around that. And this with thinner, this kind of pattern in the background is actually person moving. The person is moving actually towards the device and away from it, and repeating. Right. So if you do that, then the Doppler shift is negative and positive and negative, positive, right? So that's why you get this sinusoidal pattern of Doppler signal. And this is what we use to say that, wow, there is looks like there's some person is moving. If you actually look in details, there is this little kind of fuzzy, but this oscillation on top of this sinusoidal signal, right? Tiny fluctuations. Anybody want to guess why that is the case? This is not noise, by the way.
Is it breathing?
I'm sorry? Breathing. Oh, no, it's not breathing, but that's a good guess. Breathing, actually, if it's near enough, breathing can be detected. But in this case, actually, when a person is walking, we don't walk like smoothly in terms of your upper body. You don't move like smoothly like this. When you make a step left to right, it has the jerky move, right? So that upper body jerky movement shows up as this kind of wiggles. So that's kind of interesting signature. So the challenge of this Doppler-based sensing is that depending on the target, the human, and where the person is, the size of the body, and then what kind of clothing that they have, and absorption or things around it, the signature can vary a lot. And also the room acoustics matters. The size of the room, reverberation, absorption, even the humidity and temperature of the air makes a difference because the ultrasonic range, acoustic signal, the speed of sound and absorption gets get changed by this humidity and temperature. And also there are noises, ultrasonic noises, even fan or curtain moved by the wind, moving by the wind. or airflow from HVAC, even those subtle air fluctuations actually changes the signature. So there's a lot of false kind of negative possibilities more than you think. So these are kind of challenges that we have to overcome. Another interesting challenge is because we are the same acoustic modules for ultrasound as well as the audible applications. We have this problem called the music concurrency. This is when you play the music and the echo device playing music, and then this use present detection module is working at the same time. Then what happens is that, so on the left is the without music playing, the signature that I've been talking about, a similar kind of plot here. But with the music, when the echo devices start playing music on top of it, the same kind of analysis plot has this lot of kind of noises, kind of patterns of noises, very strong. It kind of obscures all the movement signature underneath it. What's happening is very interesting physics. Since we are using the same loudspeaker for playing just sound as well as audible sound, and audible sound, the music, the driver diaphragm is moving quite a bit. I mean, it's only maybe a few millimeters max, but still, ultrasonic frequency point of view, it's enough of movement that it creates its own Doppler shift. So that gets into the microphone. So completely dominates. And compared to what we get out of the reflection off of the person, this is much, much stronger. The signal to noise ratio is easily negative 30 or 40 dB. So we had to develop adaptive music cancellation algorithm to do this. And once that's said and done, you get the output, which you can see the kind of pattern a little bit. Still, it's not as clean as without the music case, but it's enough that our model can recognize. So now I'm going to talk about the user localization. So this is Echo Show 10, introduced 2 years ago. And this has a rotating screen. It follows the user, and this is perfect for like a kitchen island kind of application. Of course, there's a CV that tracks a person, but you also need audio-based solution because the person may not be within the field of view. So we created basically sound source localization module. And if you follow DKs, there's a lot of different approaches to this. Unfortunately, I cannot talk too much details about this because we don't have the published paper yet. I'd love to talk about this when we do. But one of the challenges is that the microphone array is very compromised compared to DKs because we didn't have much space to put the microphones. So there were 2 microphones on the front of the screen on the top, and another 2 right behind it. So separation is 5 millimeters or so. So you don't get much phase difference, which is very challenging for the beamforming and localization algorithms. And of course, we have a music playback, interfering noise, and well-known reflections are very challenging for localization, right? So there is that challenge. And ML approach, of course, requires a lot of data, and capturing that has been challenging as well. And now we're going to talk about the multiple device situation. So now we have enough of customers that have more than one Echo devices around the house. So that creates interesting problems as well as opportunities. Now, one of the challenges, what we call the device arbitration. So in this picture, let's say you are standing in front of this Echo in front of you, and let's say there's another one across the room, far away. And oftentimes, I have to admit, it's embarrassing. If you say Alexa, instead of the near one triggering, it's the far one that gets turned on, and then get annoyed, and you wonder like, is simple problem, but surprisingly, it's a hard problem. You think just measuring the SPL of these two devices and compare them would be easy? Yes, that can work well if you're very close to one device. But let's say if you're kind of in the middle of the room, you're 6 feet away from one device, maybe 10 feet away from the other device, the SPL difference is not much because of the room reverberation. And you can also think about having direct reverb ratio calculation to see whether they're close to one device or another. That's fairly kind of thin signature. It's hard to get it sensitive. And the time of arrival is challenging because Wi-Fi network is not synchronized well enough for us to do that. And then also there is not always that the near device is what you want, because if the other device is screen device, and if you request something that needs to be put on the screen, then if the device is farther away, you want that to trigger. So all those things make this device arbitration problem a little bit hard and interesting. And we had one approach that's published, which is the neural net based solution, where we have the each device running on the different neural net algorithm model that's trained to output this feature embeddings, and then those gets aggregated in cloud and then makes decision as to which one. So this is kind of end-to-end ML-based approach that we developed. And one of the opportunities for the multi-device situation is that you can think about doing multi-device-based localization and beamforming. So you have a distributed, like a micron arrays around the room. So which should make it more easier and more accurate in terms of localization problem. Yes and no, because the time synchronization again is hard. So if you don't have time synchronized signatures from different device, may not necessarily be helpful. And then locations of device not known unless you try to figure that out first. So we are thinking of ways to localize device themselves and their locations and orientations of things. And also, if you think about like training a model for this, one of the challenges is that you don't know how many devices out there necessarily. So you have to have a model that can scale depending on the number of devices and micro array channels. And multi-device ASA, I'm going to skip this one. I feel like I need to manage time a little better. So now the robotics, we introduced Astro earlier this year. So it's an interesting kind of opportunity. Now we have this echo device with the sensing mechanisms running around the house. There's some challenges to this in terms of supporting all these existing algorithms and use cases that I talked about. Since the microarray is moving around, it can rotate. The beamforming, is hard because you think about where is the reference point. There's this global reference point in the house, and then there's a local reference point while the device is rotating or moving. And then AC has harder time converging because the transfer function is constantly changing. And then if you move along the walls or corners, the reflection has Doppler shift. It's a linear kind of error. And then road noise, with whatever road noise getting to the microphone. And also the SSL is super important because you call this Astro from far away, you want it to come near you, right? You don't want it to go somewhere else. So the SSL is super critical. But on the other hand, the opportunity is that this can go around the house and then do a slam of the room. So you may have a map of the room with you, and can you take advantage of that information for acoustic sensing applications? And then this sensing data from this moving robot can be used with a static sensing signal from the local device, and then we can have collaborative kind of sensing mechanism here. So now I'm going to talk about some of the future work, things that we haven't completed the work and it's not out there, but problems that we are thinking about. So it's sort of set of questions that we are asking ourselves. And this is where I think I can get some help from you guys in academia or other institutions about kind of UN more challenging, interesting problems to solve, which can benefit us and consumers in the future. So one is online learning. In the beginning of Alexa and Echo and some other, competitive device as well, the paradigm was cloud. It's all about cloud, right? We send the signal to the cloud and then do the processing with the big compute and big model. But now paradigm is shifting a little bit. Now there's more emphasis in doing local for a few reasons. One big reason is privacy. A lot of people don't want their data to be uploaded to the cloud. So as I mentioned, we are even IASA and NLU, we have local version that's running because of that reason. But the other is that cloud is necessarily free of cost and complexity. It has a lot of computation cost as well as a network bandwidth limitations and things like that. So it's not reason why local kind of processing is valued. But of course, the challenge is that local has a limited compute, so your model is going to be small. So your model is not going to generalize enough. And that's the reason why if you can do online learning and adapt to local environments, such as reverberation, room size, maybe nearby surface reflections, if it's nearby the boundaries, and there might be some household specific noises, or people who use device in that room can adapt to it, right? So these are the things that we are thinking about, making this device local centric, but still very capable and highly accurate. Also, we are thinking about detecting the room geometry. Because if you have distributed acoustic sensors around the house, even moving one, can we figure out the geometry of the room? Also, can we figure out the location of the device to the room, right? So if we had that kind of capability, I think it can help detection and localization and online learning and beamforming applications. Also, acoustic sensing is one of them. I've been talking about this, but that's not the only one. It's hard not to take advantage of camera and RF, because a lot of devices have them already. And acoustic, of course, sensing, ultrasound I talked about, it's nice because it's always in the background. It's also active. It's not intrusive. But for audible range, we can just passively sense things with the people's activities. So try to kind of take that into some kind of information. The camera is very nice in a sense that it's the most accurate one, right? If you can have it. You can, in some detecting objects and humans, but because of privacy and narrow field of view, it's not always available. On RF, maybe some of people in the room might be more expertise on this than me, but I'm not talking about any like dedicated millimeter wave sensors or ultra wideband, but existing one that's in cheap, Echo products. So Wi-Fi and Bluetooth, take advantage of that, and that's one of the things that we are looking into. And of course, the challenge is that it's not as precise because the Wi-Fi and time of flight information not as necessarily available. We can't really control the router. Bluetooth has its own lot of limitations. So those are some of the challenges. And also we think about the fusion of these things, how we can fuse these different sensors together better. And because they complement each other. And there's early fusion versus late fusion. Right? Early fusion is more theoretically more promising, but it requires large model, large data. Late fusion is much easier, but it may not be as capable because it doesn't have as much correlation of different sensors. And so we think about some kind of mid fusion where we do some fusion engineering up front and then have one model that can do the detection and classification of things. So lastly, ML, like machine learning is the way to go for the more higher intelligence, more complicated kind of applications. And it's more future-proof way because you can learn and adapt and better over time. But as always, this data is challenging. Data is always challenging. Even for us, like a big company like Amazon, you think we have a plenty of data. It's yes and no. We have lots of data for the existing devices features. But any new features or new devices, we still have to start from scratch, collect the data, bootstrap the model. So data is always a bottleneck in terms of the efficiency of working on these solutions. So the solution that we are thinking is one of the big emphasis is trying to synthesize the data based on the simulation of physics. So this is my last slide. So we have set of like modeling kind of technologies that we've been developing to model the room acoustics as well as the microphone array and even loudspeaker down to electromagnetic mechanical component, so that we can model all those things. Holy grail is that in just a virtual reality kind of world, we model all the sensors and humans and moving around, and we can collect the data and we use that to train the model. So that's kind of where we are going towards. Okay, with that, I guess we have exactly 5 minutes, but I can't take some questions.
Sharing all the various problems and challenges that we as people in academia can work on and see that what you work on as application in your work. So I would invite the audience for questions.
I have a question, yes, but there are
I have a little hard time hearing, but I will try. It's a lot of reverberation.
sorry.
There's a lot of reverberation, but I will try my best to understand the question.
Wontak, can you hear me? Can you hear me speaking from here?
Yeah, I can make out the speech, I think. Intelligibility a little low, but I will try. So please go ahead.
Can you hear me from here?
Oh, that's much better. Thank you.
Okay, I guess we will go with this mic. So first of all, Wontak, thank you for the fantastic talk. So I want to first say that we heard from the Mobius's keynote that we are creating technologies that can turn magic into reality. And I think when the first Alexa Echo came out, it was pure magic to many of us. So it's a real treat for all of us here to have you with us and telling us about the history of Alexa and the inner workings of Alexa. So thank you so much. I have a question. Actually, I was thinking of asking you whether you could use these Alexas to do some sort of SLAM, right? Sort of room mapping. But in your talk, I think you already said that is exactly what you're working on. So I have I guess a related question. I believe Amazon is also working on things like the Ring, right? There's this drone device. So I'm wondering, what are your thoughts on potentially combining Alexa and some of the functionalities that you described with a mobile platform, such as the Ring drone, or maybe even a robotic vacuum, sort of a mobile device that can, both sense and listen and perhaps perform various of these magic. Do you have some thoughts about that potential, I guess, direction?
Yeah, I mean, I cannot speak about any specific like a future products or features, but it is very enticing kind of thoughts for us, combining the mobile device, which has a better kind of sensing capability in terms of diversity of the data within the house, whereas a fixed devices can only sense things around them in fixed, whereas this mobile device can go on different parts of the house and get all the information. So it's in the very much in our interest to kind of combine this local static kind of sensing signal with the mobile one to create the better intelligence around the house and maybe mapping of the house and other information that we can use to create some different features. So yeah, it's very much a big interest of us to do that.
Thank you so much.
Thank you.
Hi, Wontak. Thank you so much for presenting it. Wonderful presentation. We get to learn a lot. Nirupam Roy, UMD College Park. I have a question. So, what amazing to me for voice assistant Alexa is that it has created a new natural interface with the machine world with human directly. And going forward, we can imagine that every devices or this environment would be full with a small energy harvesting sensor, and probably voice can be one way to interface with them. Several challenges and hurdles are on the way, although because running voice detections, event detections, acoustic sensing on energy harvesting standalone devices can be challenging, and we see some traction in academia in that, including my own group. What do you feel about what are the traction in industry along that line?
Sorry, I didn't follow 100%, but you were asking about the energy harvesting. And the,
Yeah, I'm asking about how about what are your take? What is your stand on enabling voice assistance on completely energy harvesting devices?
That's something I'm not directly. I don't know much about that activity. If there is I'm not directly involved with that energy harvesting side of things. So it's possible that there might be some activity in Amazon, but I'm not really involved with that energy harvesting side of things.
You mentioned about voice detections and speech detections on embedded system without requiring cloud to process that voice. One step forward to that, can we have standalone battery operated or even energy ambient powered devices to have similar capability? What do you think about that?
Yeah, I mean, right now our devices are local, but still requires a power plug into the wall. Not having to have that or very small battery operated device much better. And I believe some of the Ring cameras run on the batteries completely for a year or more, I heard. So it's very much in our interest, but I'm more focused on like actual sensing side of things in terms of batteries and energy harvesting is something that I'm not as familiar with.
Sounds great. Thank you.
Thank you.
Hello, Wontak. Thank you so much for the nice talk. I'm a big fan of Alexa. I have my first Alexa since 2015, and I have different generation of it and the Ring devices. So I think one problem I'm facing right now using all those devices at my home is I feel like, okay, I implemented like a lot of Ring sensors, right? Like the motion sensor, the contact sensor, like the cameras. But I feel like if they could localize each other with Alexa, that might be really helpful for me to identify where I am, and Alexa can be more smarter instead of just doing like the skill set, doing the routine in the Alexa app. So I'm just like wondering like what's your thoughts, like envisioning like how could all those, for example, existing like off-the-shelf device that could like work together to enable a like smarter home.
Oh yeah, that's very much of our interest, and some of my talk was about that. Right, if you have more than one device around the house, it's very much kind of in our minds that we should be able to know more about where you are and where the devices are, and with that information, I think we can serve better information to you. We know when you try to interact with Alexa, hopefully we know exactly which device to work with, and then also we know your intention better by knowing where you stand and whether you are in the kitchen or living room, right? You may have different kind of activities or information that you need. So by knowing where you are in the house and maybe time of the day you might be doing different activities, if you can learn that, we can serve different information. In the morning, you may be, making breakfast in the kitchen. You may have certain kind of music or certain kind of news that you want to hear. If you can automatically figure those things out and then serve the right information, I think that can delight the customers. So yeah, we are very much in just providing that kind of services. Thank you.
So I want to get Basima again. I'll ask one last question, and after that, we will take a break before the next session. So we have talked, we have answered questions, and in the last slide, you talked about data, and we talked about having different devices. So my question is that when you have all these different devices and new devices coming up, so there is a device diversity. So how your algorithms or techniques handle that? Do you develop algorithms that work for all the devices, or you collect data from every different devices and then work on develop algorithms for each of them?
Oh, that's a very good question, and something we deal with the challenge all the time. So the thing about what's good thing about old-fashioned DSP algorithms is that it can generalize better. So when the device changes, micro rate or geometry changes, and number of microphone changes, we require some data for validation and some tuning for it. But largely, it's much easier to kind of adapt an algorithm for that new device configuration. For machine learned CNN models, a little different story. You still need lots of new data to adapt to it. And so that's one of the challenges, as I mentioned in the here, is that ML sounds great and then you can do so much things, but in terms of scalability, adapting to different kind of hardware configurations, especially if ML model takes advantage of multiple channels, not single channel, then the data requirement doesn't go away, even if you already developed the model and try to scale up. So it is kind of trade-off, depending on the situation, depending on the features and your timeline of development and the accuracy that requires. We kind of entertain both approaches and pick the appropriate one. But as I said, in the future, we want to do more machine learned approach, provided that we can have enough of training data, whether it's collected or synthetically generated. And synthetically generation, of course, is much easier once you have the technology. So that's kind of where we are going towards.
Thank you so much for answering. Thank you so much for joining us and giving amazing talk. A big round of applause for Wontak.